But the indirect effect is positive because the predator is also consuming the resource of the competitor. And I haven't done this in a while. We look at the indirect effect of these two on each other, right? So this consumer is, what's the indirect effect of the consumer on its predator?
Negative.
Yeah, positive.
And this indirect effect is negative. Because basically this is, the indirect effects make them kind of like resource competitive because they share resource. So this is called omnivory.
So if the predator's eating the consumer, what exactly is the concept of the indirect effect there?
So the indirect effect is the pathway through the resource. So what is the effect of the species P on consumer via the pathway of the resource? So by potentially reducing the resource, it reduces the amount of food available for the consumer.
Oh, because the predator is eating the resource as well.
Yeah.
If you look at in all these, the back and forth, right? So like from like P to C back to P, is that a way to look at like interest-specific competition?
Yeah. So that's basically, you can show, yeah, that's exactly right. You can show the indirect effect of the predator mediated to its consumer, the interest-specific competition.
But then if you have like a mutualism, then it's all positive.
In the predator-mediated competition, is there no indirect effects between the two consumers?
Yeah. What are they? How many indirect effects are there? There's two pathways, right?
Yeah. So 4 different indirect effects.
And what are their signs? Look back at these. They're the same pathways that we looked at here.
Oh, okay.
So they're negative.
Yes.
The indirect effect of on the right side of the predator on the resource, is that an X or is that a plus? On
It's a
the right
plus.
side? Oh, got it.
So now, these are all the possible interactions with 3 or 4 species. So, but there's a lot of, you can already see there's a fair number of indirect interactions, and things rapidly become highly complicated. And this issue has really plagued food web ecology. And so what we're talking about today is sort of this impressive yet really interesting field of food web ecology. We've tried to deal with this complexity in various ways. And we've made progress, but it's halting and it's very difficult. So first off, the focus. This is one of the more complicated webs that's been denoted. This is the North Atlantic food web. It was focused on cod, and their main prey species, capelin. One of the questions that was asked in this, and I'll talk about a simpler version of this, was there's been some thought that cod recovery since the collapse of cod has been caused by, there's been a rapid increase in carp seals population, and there's a strong correlation between these two, and carp seals can't eat cod. So there's been some thought to culling seals to release the cod from a possible low density. And this paper pointed out the fact that, well, if you want to look at this, you're going to have a really hard time figuring out what the sort of net indirect effect is. I said, I'll go into this much more. So I want to talk about, so we've gone from sort of having all these possible different indirect effects to these really highly complicated food webs. I just want to talk about how we talk about these. And just some statistics we use. So some of the statistics that have traditionally been used in these food webs to sort of try to differentiate amongst different food webs, try to make predictions about food webs. Because once again, we're really interested in species richness. We have been. What causes richness within food webs? What are the effects of food webs? When I talk about the paper I assigned about food webs and species richness and stability, we'll talk about this. Richness is it's thought to be a major driver of things. Another statistic that's been used is connectance. Connectance is the proportion of possible links that exist within a food web. So, how many possible links are there? Food web links.
Which is factorial or something?
I think it's factorial. I'm actually, I think it's actually on the order of 2 to the n minus 1. Or that's minus 1. I could be proved wrong.
That's a lot.
There's 2 possible ones there. These are all feeding links.
So we're assuming the possibility of them eating each other, so
Yeah.
there's one going each way. Okay, that makes sense.
Do I got it all? That's 6. Is it n squared? No. It's 10. No, I won't do that. But, so connectance is just the maximum number of links. The number of links divided by the maximum number of links. And of course, the maximum number of links go up as it's n squared, isn't it? Minus 1. Someone can figure it out. But as the number of species increases, the possible links for the number of links for each individual species increases at that same rate, right? So if you have 10 species, each individual could eat 9 different species. If you have 20 species, each individual could eat 19. So the possible number of links increases dramatically with the number of species. So connectance, in some ways, could vary in ways, yeah.
So the maximum number of links is determined by 2 to the s minus 1.
And I can't remember what it is,
Okay.
but someone could do the combinatorics with it. A lot of you figured it out yet?
2, 3, and 4 fits factorial. But
Is it factorial?
it fits that. There's 3, but I've gone higher order.
All right.
Just do it.
Someone could do that too. We're going to think. I can usually think on it. So those have been the sort of the main ways of characterizing food web. There's also been ways you can think about the maximum number of trophic levels. So one way you can sort of think about, you can measure trophic levels by measuring the number of pathways that go between a basal resource. So these are called basal species here because they don't have any incoming links. They represent autotrophs and plants and such. And then you can measure the maximum trophic level, which I'm going to talk about trophic level. But I think like maximum trophic level, you can measure average trophic level. You can measure the proportion of species that are basal species, and so on. One of the things that starts to happen, and if you look at the top of this food web, you see some well-resolved species. You see cod, you see seals. As you go down further, you see species like lobster, shrimp, squid. These aren't really species, these are taxonomic groups. So we start talking about what are called trophospecies. And one of the things we're going to talk about repeatedly is that the data for food webs it's really hard to resolve them fully. And so based on the difficulty of studying organisms, measuring organisms of different types, ecologists will frequently just lump them into trophospecies. Down here we have plankton, copepods. Sometimes they're just grouped taxonomically, but sometimes you can just group species by what they consume. As they consume the same species, then you can call them a trophic species, and are consumed by the same set of species. So these are food webs. There's been a recent interest in adding more interactions, but I'm going to be talking about food webs in general because that's where most of the work's been done. This is a mutualism web that's been done. In this case, this is a quantitative mutualism web. These are a set of different plant species. The width of the black bar here represents their relative abundance. So each one of these letters represents a different species. G and O are common. P, Q, and R are relatively rare. On the top are all the different pollinators of those plants. And once again, the width is their relative abundance. We have beetles, dipterans, flies, and in this case, they're almost all hoverflies, hymenopterans, which are wasps, and ants, and then lepidopterans, which are butterflies and moths. So the width is their abundance, and the relative width of these links, then, is the relative interaction strength. So how often do these different species visit the other plant species? So we can make progress both in these types of mutualism webs, but you can do the same thing for food webs if you can make some sort of quantitative estimate of the diets of different organisms. It's a bit easier with something like a constrained web like this mutualism web. These are basically the number of visits calculated over a certain amount of time. When you start talking about food webs, you have to measure the diets of species at really different trophic levels. Sometimes you can measure diet directly by observations. You can also measure diet by examining gut contents. In this case, there's actually quantitative estimates for these, and you can, for fish especially, you can get gut contents very easily because you can make fish vomit, and you can just count what's in their guts fairly easily. You can make observations on things like seals. But when you get lower down this trophic, in these trophic levels down here, we're talking about things like squid, and shrimp, and scallops, and stuff like that. There's some observational data that can be used to make general predictions of what the relative strengths are.
Maximum number of links is n squared minus n.
Okay. There we go. Thank you.
Also known as n choose 2 times 2.
All right. See, this goes up. Basically, the point I was trying to make badly was this goes up like the square species richness. Whereas, if you think about the number of links, if connecteds was to remain constant with species richness, then the number of links per species would have to go up like the square too. So, anyway, I want to tackle this question of, so this is the idea, getting back to this whole problem of general uncertainty in trying to predict what's going on. So this is a different marine food web. This is off the Benguela current system off the coast of South Africa. There were thoughts that they, in this case, would cull the South African fur seal to increase the catch of a whole bunch of fish that were part of the fishery.